Have you ever stood in the profound quiet of a garden, perhaps in the heart of Kyoto, as dusk settles, and felt a stillness so deep it seems to penetrate your very bones? A silence where the only movement is the slow unfurling of a fern or the drift of a single red maple leaf. In that moment, the world feels utterly, perfectly still. And yet, this feeling, this deep and resonant calm, is perhaps the greatest illusion ever conceived. For in that silence, you are moving. You are being carried on a journey of impossible speed and scale. The very ground beneath you, the ancient stones of the garden path, the roots of the silent pine tree, are all turning. They are spinning on the surface of a world that rushes forward at a speed that would outpace the wind, a velocity that could cross the entire archipelago of Japan, from the snowy fields of Hokkaido to the warm shores of Okinawa, in the space of a single hour, 1,000 miles an hour, and yet the koi in the pond below do not ripple. Your breath does not catch, your heart does not tremble. And this planet, our Earth, is itself only a single grain of sand in a much larger current. It is falling, endlessly falling, in a graceful arc around our sun, a star 93 million miles away. We are orbiting that star at a speed that defies comprehension, nearly 67,000 miles per hour. Imagine the fastest bullet train, the Shinkansen, a silver blur of motion. Now imagine a speed 100 times greater than that, a silent, ceaseless flight through the absolute vacuum of space. And even that is not the end of the journey, for our entire solar system, our sun and all its children, is adrift in a galactic river. We are sailing through the arms of the Milky Way, our home galaxy, at almost 500,000 miles per hour, a spiraling city of stars, itself turning in a slow, cosmic dance that takes 230 million years to complete a single revolution. And still, you feel nothing. You are frozen, in a universe of unimaginable motion. How can this be? What is this profound stillness we experience, if not the truth of our existence? What if this feeling of calm is a story our senses tell us, a gentle lie to shield us from the dizzying reality of the cosmos? What if time itself, the steady ticking of our lives, is merely the echo of a much deeper rotation, a spin that began before the first atoms were forged, before the first photon of light ever traveled through the darkness, before there was anything like memory to record it? Tonight, we will not fight this current. We will drift into that mystery. We will let go of the shore of our perceived stillness and float into the spinning heart of everything. We will ask not just why things move, but why it seems that nothing in the universe can ever truly stop moving. So, find a quiet place. Close your eyes. Let the world you think you know fade away. Feel the gentle weight of the air on your skin, and imagine it not as stillness, but as the perfect harmony of everything moving together. Let the sound of my voice be a guide, a whisper to follow into the deep and swirling mystery of it all. Before we begin our descent, if you feel so moved, a gentle tap on the like button or a quiet subscription to this channel would mean more than I can say. It is such a small gesture in the vastness of the digital world, but I hold each one with a deep and personal gratitude. Every bit of your support is like a distant star adding its light to this tiny constellation, keeping this small universe alive and reminding me that these quiet stories still find their way to gentle hearts like yours. Thank you. Now, let the journey begin. Let us start with that first, most intimate paradox, this illusion of tranquility we inhabit. If every single thing in the great cosmic ocean is spinning, why do we feel so perfectly, so profoundly, frozen in time? The world beneath your feet is a grand and silent engine of motion. It turns and turns and turns. A constant and unwavering spin that has defined the rhythm of this planet for more than 4.5 billion years. At the equator, that invisible line that wraps around the Earth's waist, the surface rushes through space at over 1,000 miles per hour, faster than the speed of sound. A speed that would tear the air into a screaming gale if the air were not moving along with it. It is caught in an eternal, graceful orbit around the Sun, a journey of nearly 600 million miles that it completes once every year. To stay in that orbit, it travels at a speed of nearly 67,000 miles per hour, a velocity so immense that in the time it takes you to draw a single, slow breath, you have traveled nearly 20 miles through the void. And as you exhale that breath, the entire solar system continues its own pilgrimage, a silent voyage around the colossal, spinning heart of the Milky Way galaxy. We are all passengers on this stellar arc, sailing at a speed of almost 490,000 miles per hour. And yet, here you are. Perhaps you are lying in your bed, the sheets perfectly still around you. Or maybe you have a cup of warm tea beside you, its surface a perfect, glassy mirror reflecting the soft light of your room. The coffee in your cup does not ripple. The delicate web of a spider in the corner of the room does not tremble. The stars, when you look up at them, appear as fixed and eternal as diamonds pinned to black velvet. It is one of the most profound illusions of existence, a deep and beautiful paradox of absolute motion and absolute calm. From the smallest, most infinitesimal particle to the largest imaginable supercluster of galaxies, everything in this universe spins. It is a fundamental law, a cosmic signature. The electrons within the atoms that make up your body are not static points. They exist in clouds of probability, possessing an intrinsic property, called spin. The atoms themselves rotate. The planets revolve. The moons orbit the planets. Stars are born from vast, swirling clouds of gas and dust that collapse inward, spinning faster and faster until they ignite. And the galaxies, those breathtaking islands of light, twist in vast, silent spirals, their arms tracing the memory of some ancient, primordial motion. Some cosmological models even suggest that the universe itself, on the grandest of all scales, may possess a subtle, global rotation, a faint twist written into the very fabric of space-time. But why? Why, if everything is in constant, dizzying motion, do we feel so irrevocably still? The beginning of the answer is a whisper, a quiet principle that governs all of motion and non-motion in the cosmos. It is a concept known as inertia. It was first given a name and a clear description by the great physicist Isaac Newton in the 17th century, though its truth has been felt by every object since the beginning of time. He wrote that an object in motion stays in motion, and an object at rest stays at rest, unless it is acted upon by an external force. This simple, elegant law holds the secret to our perceived stillness. We do not feel the Earth's endless spinning for one simple reason: we are moving with it. We are not separate from its motion. We are a part of it. Your body, the house you are in, the air you are breathing, the vast oceans and the towering mountains, all of it, every single part of this world, turns together. We are locked in a single, silent, unified rhythm. To feel motion, your senses require a change, a difference. You need to be pushed or pulled. You need to accelerate or decelerate. Imagine yourself on a Shinkansen, the Japanese bullet train. As it sits in the station in Tokyo, you feel its stillness. Then, as it begins to move, you feel a gentle but firm pressure against your back. That is acceleration. Your body, which was at rest, is being forced into motion. But once the train reaches its cruising speed, traveling smoothly along the rails at 200 miles per hour, that feeling of pressure vanishes. You can stand up, walk down the aisle, pour a cup of tea. The liquid in your cup will be as still as if you were in your own home. You and the train and the air inside it are all moving together as one. Your body is in a state of uniform motion. You only feel the movement again when the train slows down as it approaches the station in Kyoto, or if it suddenly sways or jolts. You feel the change, not the constant speed. The Earth's motion is the most perfect, seamless bullet train imaginable. Its spin is almost perfectly constant, a smooth and ancient glide that has barely changed over millions of years. It was spinning at this same gentle rate when the first humans looked up at the stars and saw them wheeling across the night sky. There is no vibration, there is no sudden lurch or jolt, and because space is almost a perfect vacuum, there is no air friction to rush past our faces and remind us that we are hurtling through the cosmos. There is nothing to push against us. We are moving with the river, not fighting its current. Astronauts experience this same illusion on an even grander, more sublime scale. Aboard the International Space Station, they are traveling at a breathtaking 17,500 miles per hour. They circle the entire planet once every 90 minutes, witnessing 16 sunrises and 16 sunsets in a single Earth day. Yet, inside their spacecraft, everything is calm. Objects float in weightlessness. But there is no sense of rushing forward. Without the resistance of an atmosphere, without the familiar pull of gravity defining up and down, their constant, high-velocity motion feels exactly like stillness. This profound phenomenon, this uniform motion, is the same principle that allows you to sip your tea on an airplane traveling at 500 miles per hour. You, the cup, the tea, and the plane are all moving as a single system. You only become aware of the immense speed when turbulence strikes a sudden change in air pressure, an unexpected force that interrupts that perfect uniformity. Only then do you feel the movement. The motion of our Earth is seamless. It is a waltz, so perfect that the dancers have forgotten they are even moving. We are on, as the great science communicator Neil deGrasse Tyson once so beautifully said. A space rock that is orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home. It is so easy to forget this cosmic journey because our senses were simply not designed for it. They were never built to perceive motion on such a colossal scale. Our inner ears, the delicate, fluid-filled chambers that give us our sense of balance and motion, evolved to handle the small, everyday movements of life on a planet's surface. They are exquisitely sensitive to the acceleration of walking, the sudden stop of a fall, the gentle sway of climbing a tree. They respond to changes in velocity, not to a steady, constant speed. That is why you feel the lurch when a car starts moving, but you do not feel its constant speed as it cruises down the highway. On Earth, everything moves with you. The very air you breathe is carried along in the same rotational dance. There is no start or stop to our planetary motion on a human timescale, only an eternal, silent glide. We were born into this motion. It is our natural state. To us, it feels like rest. And yet, for all our sensory limitations, the quiet and patient minds of scientists have found ways to measure this hidden motion, to prove that our world is indeed turning without ever needing to look at the stars. The most elegant proof of this is a simple and beautiful device, the Foucault pendulum, first demonstrated in the heart of Paris in the year 1851 by the French physicist Léon Foucault. It is a heavy pendulum suspended from a great height, allowed to swing freely back and forth. If the Earth were still, the pendulum would swing in the same plane forever, but it does not. Over the course of hours, the direction of its swing appears to slowly, majestically rotate. But it is not the pendulum that is turning. It is the floor beneath it. It is the museum, the city, the entire planet that is slowly, silently spinning under the steady, unwavering swing of the pendulum. It is a device that does not need the sun or the stars to prove the Earth's rotation. Its slow, graceful twist over hours is the planet's spin made visible, visualized in profound silence. If you have ever had the chance to stand before one of these pendulums, perhaps in a quiet museum hall, you have witnessed time and motion merging into one. Each gentle swing is a tick of a cosmic clock, a quiet confirmation of the great dance we are all a part of. The pendulum is a silent oracle, whispering the truth of our motion to anyone patient enough to watch. On a cosmic scale, this rotation is far from trivial. It is the very engine of our world. The Earth's spin, is what defines the fundamental rhythm of our lives, day and night. It is what stabilizes our planet's powerful magnetic field, an invisible shield that protects us from the harsh radiation of the sun. Without this spin, our world would be a desolate, lifeless place. One side would be scorched in perpetual, unbearable sunlight, its oceans boiled away. The other side would be frozen in an eternal, absolute darkness, its atmosphere turned to ice. Life, as we know it, could not exist in such a world of extremes. The scientists at NASA's Goddard Space Flight Center, who study the intricate mechanics of our planet, have noted that the Earth's rotation has been gradually slowing over billions of years. This gentle deceleration is caused mostly by the gravitational pull of our moon, a constant tidal friction that acts like a subtle brake. The effect is minuscule, adding about 1.7 milliseconds to the length of a day every century. So even within our feeling of perfect, constant motion, there is change. A slow, invisible, but very real evolution. The heartbeat of our planet is gradually slowing down. When we look deeper, beyond our own world, we see that rotation is not just an earthly phenomenon. It is a cosmic signature, a universal language. Stars are born from the collapse of vast, cold clouds of gas and dust. And as these clouds shrink under the relentless pull of their own gravity, they begin to spin faster and faster. This is due to a fundamental principle known as the conservation of angular momentum. It is the very same law of physics that makes a figure skater spin with dizzying speed when she pulls her arms in close to her body. As her mass becomes more concentrated, her rotational velocity must increase to conserve her total angular momentum. Every planet in our solar system, including our own, inherited this momentum from the Proteus, swirling disk of material that formed our Sun. The Earth's 24-hour rotation is a fossilized trace of that ancient, cosmic whirlpool, a memory of our own creation. Even the Sun itself spins, completing a full rotation roughly once every 27 days, dragging its vast magnetic field through space like glowing threads of silk. And our galactic home, the Milky Way, is also turning. It completes one majestic rotation every 230 million years, carrying its hundreds of billions of stars in a grand, spiral dance that began long before our planet even existed. The James Webb Space Telescope, that golden eye gazing into the dawn of time, has captured images of galaxies so far away that their light has traveled for over 13 billion years to reach us. And even in those primordial galaxies, those first islands of light in the young universe, astronomers see the telltale signs of rotation. Scientists from the European Space Agency, studying these early formations, have found subtle differences in the light from opposite sides of these galaxies. One side appears slightly red-shifted, meaning it is moving away from us, while the other side is slightly blue-shifted, moving towards us. This is the unmistakable signature of spin. It seems that the tendency to rotate is not something the universe learned. It is written into its very DNA. But how can all of this be? How can everything be spinning, and yet we feel so profoundly, so peacefully still? Part of the answer lies in one of the most beautiful and revolutionary ideas in the history of science: relativity. According to Albert Einstein, there is no such thing as absolute motion. There is no fixed, universal reference point from which to measure all movement. All motion is relative to something else. So, from our perspective, standing here on Earth, we are at rest. We are the center of our own reference frame. And from this vantage point, it is the universe that moves around us. The sun rises and sets. The stars wheel overhead. From the perspective of an observer on the sun, however, the opposite is true. They would see the Earth as a small blue marble, spinning as it orbits. Both perspectives are equally valid. There is no absolute truth about who is really moving. This profound symmetry is what keeps the laws of physics consistent everywhere in the universe. and it is what makes our feeling of stillness an illusion of perspective. In the deep void of space, the astronauts aboard the International Space Station are orbiting the Earth at nearly 5 miles per second, a speed that is almost impossible to imagine. Yet they experience weightlessness, not motion. Their subjective sense of down changes every moment as they circle the globe, yet their minds adapt to this new reality. We, too, are passengers in constant motion, and our minds and bodies have adapted perfectly to the calm. Our stillness is a form of survival. It is a delicate balance between what our senses can bear and what the vast cosmos demands. If we could somehow feel it all, the dizzying spin of the Earth, the relentless pull of the sun, the ghostly drift of the galaxy, our perception of reality itself, our sense of time, would likely unravel. Because motion and time are not separate things. They are deeply, inextricably intertwined. The rotation of our planet defines our days and years. The orbit of stars defines the heartbeat of the cosmos. Time, as the great astronomer Carl Sagan once said, is woven into the very fabric of the universe. And we are the thread. The quiet you feel right now is not the absence of motion. It is the sublime harmony of everything moving together. So when you lie down tonight, beneath the invisible turning of the stars, remember this: you are not standing still. You are not at rest. You are gliding. You are drifting through a silent, cosmic river, gently, constantly, endlessly. Each moment of stillness you feel is just the universe, moving too smoothly, too perfectly, for you to notice. And in that perfect, silent balance of motion and calm, life finds its quiet rhythm. Take a slow, deep breath. You are spinning. You always have been. And the silence you hear is the sound of everything, everywhere, moving together as one. But as we drift deeper into this story of motion, our thoughts must turn backward beyond our own existence, beyond the formation of our planet, to the very first moment before motion as we know it began, when the universe itself, a point of unimaginable energy, took its first breath, its first turn. For it is there, in that singularity of origin, that our next question begins. If you could rewind time, not just by centuries or millennia, but all the way back through the age of stars, back through the formation of the first atoms, to the very first infinitesimal second after the Big Bang, what would you see? Would there be light? Would there be sound? Or would there only be a sudden, incomprehensible motion? A swirl, a twist, the very first rotation of everything that would ever come to exist? The question of who, or what, gave the universe its first spin is not a question for philosophy alone, but one that lies at the very heart of modern physics. The answer, if it exists, is buried deep within the complex equations of cosmology, hidden inside the earliest, most fleeting moments of time, when matter, energy, and space itself first began to unfold. Astronomers and physicists refer to this initial period as the Planck era. It is a window of time so incomprehensibly brief, lasting for just 10 to the power of negative 43 seconds after the Big Bang, that our current laws of physics break down. We cannot fully describe it. It is a realm where gravity and the quantum world merge, a place beyond our current understanding. But what little we can infer from the echoes of that moment suggests something extraordinary. The universe may have been born, not in silent, uniform expansion, but in a gentle, primordial rotation. Today, scientists who study the cosmic microwave background, that faint, ancient afterglow of the Big Bang, a soft whisper of light that permeates all of space, have found clues. Using incredibly sensitive satellites, like the Wilkinson Microwave Anisotropy Probe, or WMAP, and its successor, the Planck satellite from the European Space Agency, they have mapped this relic radiation in stunning detail. They have found that it is incredibly uniform, almost the same temperature in every direction you look. But it is not perfect. There are tiny irregularities, small ripples in temperature only a few millionths of a degree apart. These patterns are of monumental importance. They tell us that the early universe was not perfectly smooth. There were slight differences in density and energy, and it was these tiny imperfections that, over billions of years, grew into everything we see today. Gravity pulled on the slightly denser regions, gathering matter together to form the first galaxies, stars, planets, and eventually, life itself. But some researchers noticed something stranger within these patterns, something that was not supposed to be there, a faint alignment, a kind of large-scale twist in the distribution of those hot and cold spots in the ancient light. It was a mysterious pattern that seemed to suggest that the universe, on the very largest of scales, might have a preferred direction, a preferred axis of rotation. For a time, it was playfully, and perhaps a bit nervously, called the axis of evil. Not because it was sinister, but because it challenged the deeply held assumption that the universe should be the same in all directions. According to the data from NASA's WMAP mission and the follow-up observations by the Planck satellite, this strange alignment could mean one of two things. It could be a subtle artifact of our measurements, a statistical fluke that will disappear as we gather more data. Or it could be the first real evidence that the entire universe, in its infancy, once spun. If that is true, then that primordial spin might have shaped everything that followed. It could be the reason for the graceful spiral arms of galaxies, and it might even have set the very direction of the arrow of time, the reason why time flows forward and not backward. But how could such a universe-spanning rotation even begin? The key might lie in the strange and wonderful world of quantum mechanics, in something called quantum fluctuations. These are tiny, random, and spontaneous changes in the amount of energy at a single point in space. Even in a perfect vacuum, what we would consider complete emptiness, these fluctuations are constantly happening. The quantum world is never perfectly still. As the scientists at NASA's Goddard Space Flight Center describe it, quantum fields are never at rest. They jitter. When the Big Bang happened, the universe was smaller than an atom. In the first fraction of a second, it underwent a period of brief but explosive expansion, known as cosmic inflation. In this moment, the universe grew faster than the speed of light, stretching those tiny quantum jitters and amplifying them to cosmic scales. That rapid, violent stretching could have turned some of those random quantum fluctuations into swirling, rotational motions. The very first cosmic spins. The theory of inflation, first proposed by the physicist Alan Guth in the year 1981, explains why the universe appears so smooth and uniform on large scales, yet still contains the tiny seeds of structure that grew into galaxies. But in more recent years, incredibly precise data from the Planck satellite and ground-based experiments like BICEP-2 have suggested that, during inflation, subtle rotational modes, known as B-modes, may have existed within the primordial gravitational waves. These tiny curls in the fabric of space-time could be the fossil record of the universe's very first rotation. They seem to show that the Big Bang was not just a simple explosion outward from a single point. It was a twisting birth, a swirling genesis that imprinted the property of spin across every scale of matter for all of time. And this idea makes perfect, intuitive sense when we look at what happened next. As the universe continued to expand and cool, matter began to form. First, the fundamental particles, quarks and gluons, then protons and neutrons, and finally, the first simple atoms of hydrogen and helium. Each of these particles carried with it a tiny amount of intrinsic angular momentum, or spin. Much later, when gravity began to gather these atoms together into vast clouds that would eventually form galaxies, that ancient, primordial angular momentum was conserved. It was gathered and concentrated. It is the same principle that makes a figure skater spin faster when she pulls in her arms. In the world of physics, nothing can spin from nothing. Motion must come from pre-existing motion. And so, the very first spin, however small and subtle, must have existed from the very beginning. Astronomers today believe they can see the fingerprints of that original rotation in the galaxies that populate our universe. In the year 2011, a team of researchers from the Harvard-Smithsonian Center for Astrophysics analyzed the rotation of over 15,000 spiral galaxies. They found a subtle but statistically significant preference in their direction of rotation. It was a slight imbalance, a cosmic handedness, that might trace all the way back to the spin of the early universe. While this result is not yet conclusive, it hints that our universe may not be entirely random after all. There may be a hidden rhythm, a silent, universal turn that everything, on some level, still follows. Even dark matter, that mysterious, invisible scaffolding that makes up the bulk of the matter in the universe and holds galaxies together, could carry a signature of this ancient spin. Sophisticated computer simulations, run by supercomputers at places like NASA's Jet Propulsion Laboratory, show how the vast, invisible halos of dark matter that surround galaxies twist and rotate over billions of years. They act like cosmic whirlpools, guiding the visible stars and gas within them. Without that rotational stability provided by the dark matter halos, the galaxies we see would tear themselves apart. It is as if the early universe set everything spinning, and even now, the echoes of that first motion are what keep the stars in their elegant, balanced dance. Still, the ultimate question of origin remains. Who, or what, began the spin? Physicists, when pressed for an answer, lean on one quiet and profound concept: symmetry breaking. In the earliest fractions of a second, the fundamental forces of nature that we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were once united into a single, perfect, symmetrical force. But as the universe cooled, this perfect symmetry began to break. The forces began to freeze out and separate from each other, each taking on its unique identity. When that symmetry broke, tiny asymmetries, tiny imperfections, appeared in the fabric of reality. Those imperfections, according to scientists at the European Space Agency, are what allowed structure, motion, and spin to exist in the first place. Imagine a perfectly balanced pencil, standing on its impossibly sharp point. It is a state of perfect symmetry, but it is also unstable. The slightest vibration, the gentlest breath of air, will cause it to fall, and when it falls, it must choose a direction. It breaks the symmetry. In a perfectly balanced and symmetrical universe, nothing could ever happen. There would be no reason for anything to move in one direction over another. But in a slightly unbalanced universe, a universe with a tiny, built-in flaw, it could dance. We can see the echoes of this broken symmetry everywhere we look. In the preferred direction that galaxies spin, in the way that certain fundamental particles, like neutrinos, always seem to have a left-handed preference in their spin. Nature, it seems, is not perfectly symmetrical, and that tiny, fundamental flaw is what allows everything to turn. Some scientists have even tried to detect whether the entire universe is still rotating on a grand scale. In the year 2020, astrophysicist Lior Shamir from Kansas State University analyzed the rotation of over 200,000 galaxies from the Sloan Digital Sky Survey. He found that galaxies in one half of the sky tend to have a slight preference to rotate in one direction, while galaxies in the other half of the sky prefer the opposite direction. This suggests a vast, coherent cosmic spin, a collective pattern of motion. As Shamir wrote in his paper, the universe may have a preferred direction, an axis that it follows, which began in the early universe. This does not mean that the cosmos is spinning like a child's top. Rather, it might mean that the fabric of space-time itself was twisted slightly during its initial, rapid expansion. Even a subtle twist, when stretched across billions of light-years, could cascade into the large-scale structures and motions we observe today. To us, it feels invisible, but on a universal scale, it could be the silent architect that shapes the geometry of everything. To test these incredible theories, NASA and the European Space Agency continue to map the universe in ever-increasing detail. The James Webb Space Telescope is already capturing the light from galaxies that formed just 300 million years after the Big Bang in the cosmic dawn. And remarkably, some of these ancient, infant systems already show signs of organized rotation, with spiral patterns forming far too early in cosmic history to be easily explained by chance encounters or mergers. This implies that the seeds of spin were planted almost immediately. The universe did not have to learn how to rotate. It was born turning. Even when we look down into the deepest, most fundamental level of reality, the quantum realm, spin is not an afterthought. It is fundamental. Every particle, electrons, protons, neutrons, carries an intrinsic spin. It is a built-in property of matter, described by the laws of quantum mechanics. It is not the kind of spinning we imagine in our everyday world, like a spinning ball. It is a deeper, more abstract, mathematical rotation that is encoded into the very wave function of the particle itself. As the brilliant physicist Richard Feynman once said, spin is one of the most profound properties of nature. It is not that the particle is literally spinning. It simply has spin, just as it has mass. So, in a very real way, rotation was not added to the universe later. It was part of the original blueprint of existence. When you look up at the night sky, you are seeing the inheritance of that first, primordial motion. Every galaxy's majestic swirl, every planet's silent orbit, every single photon of light that travels across the void to reach your eye, all descend from that first cosmic rotation. Without it, matter would never have clumped together, stars would never have formed, and time itself would have no rhythm, no beat. Motion is not an accident of the universe. It is its heartbeat. And though we may never know with absolute certainty what triggered that first spin, the evidence keeps whispering the same story. It has always been there, quiet, steady, invisible, yet written into the very fabric of everything we can see and touch. As the European Space Agency cosmologist Jan Tauber once said, the universe carries memory, not in words, but in patterns of light. And within those patterns lies the faint signature of the first motion, a twist older than time itself. So when we ask who set the universe spinning, the most honest, and perhaps the most beautiful answer may be this: the universe never had to learn how to move. It was born already in motion. The spin was not created, it was inherited. Take a slow breath. The atoms in your body, the very substance of your being, are still turning in harmony with that first, ancient impulse. From the tiniest spinning electron to the vast, swirling dance of the Milky Way, the same fundamental rotation continues, unbroken, for nearly 13.8 billion years. We are not separate from that motion, we are its continuation. And as we move onward through this story, we arrive at the next question, one that flows naturally, inevitably, from the last. If this ancient rotation shaped the birth of the universe itself, could it also be the very reason that life exists? Is it possible that the gentle turning of our own small world is the secret architect of our existence? That is where we turn next. Without rotation, our Earth would be a silent, desolate world. There would be no steady rhythm of day and night, no gentle cycle of seasons, no weather as we know it. There would only be a world of stark, brutal extremes. One side perpetually facing the sun, a scorched and barren wasteland where the oceans have long since boiled away into space. The other side turned forever away, a frozen and lightless desert of absolute cold, a dead world, adrift in the harsh light of its star. But because it spins, this planet breathes. Every sunrise that paints the sky with color, every wave that breaks upon the shore, every gust of wind that rustles the leaves of the trees, they all come from the same ancient, steady turn that began 4.5 billion years ago, when our world was just a molten sphere of rock and dust. It is an engine, a delicate and precise balancing act that creates and sustains everything we know as life. From the invisible magnetic shield that guards us against deadly cosmic radiation to the global cycles of temperature that nurture our oceans and clouds. Rotation shapes our world in ways both visible and profound. According to the scientists at NASA's Goddard Space Flight Center, our planet's rotation speed near the equator is about 1,037 miles per hour. It completes one full spin, not in exactly 24 hours, but in 23 hours, 56 minutes, and 4 seconds. This is what scientists call a sidereal day. This steady, reliable rhythm sets the pace for all biological and environmental cycles on Earth. Every plant that opens its leaves to the morning sun, every animal that hunts in the twilight, every great ocean current that circulates heat around the globe is synchronized to this beat. It is an invisible metronome, ticking silently beneath everything that is alive. The first, and most obvious, consequence of Earth's rotation is the beautiful alternation of day and night. This simple cycle distributes the sun's energy across the surface of the planet, preventing any one region from becoming too hot or too cold. It creates the temperature gradients that drive our winds, our currents, and our weather. Without this daily rotation, as we have imagined, one hemisphere would roast under perpetual daylight while the other would be locked in an eternal, freezing darkness. The boundary between these two extremes, a twilight zone, would be a region of unimaginable violence, a permanent wall of storms where the hot and cold air collide. It would be a lifeless world. But because our Earth spins, the sun rises and sets, and energy is shared evenly enough to allow stable climates and vast, habitable regions to exist. Rotation also has a deep and powerful influence on Earth's magnetic field, which is one of the most crucial shields for life. Deep beneath our feet, in the planet's core, lies a massive sphere of molten iron. As the Earth spins, this liquid iron core moves and churns, a vast, subterranean ocean of metal. This motion generates powerful electrical currents, which in turn create a magnetic field that extends far out into space, enveloping our planet in an invisible protective bubble. The scientists who run NASA's magnetospheric multi-scale mission describe it as a dynamo. The Earth's rotation creates the motion of molten iron, and that motion generates the magnetic field. This field deflects the solar wind, a constant stream of charged particles that flows from the sun. Without this magnetic shield, these high-energy particles would bombard our upper atmosphere, slowly but surely stripping it away, molecule by molecule, until our air was gone and our oceans had evaporated into the vacuum of space. We have a tragic example of this very process in our own solar system. Mars, the red planet, spins at a rate very similar to our own, with a day that lasts for 24.6 hours. But Mars is a smaller world, and its core has cooled and solidified long ago, without the churning of a liquid metal core. Its magnetic dynamo has shut down. Without a working magnetic field to protect it, its once thicker atmosphere and surface water were slowly eroded by the sun's relentless radiation over billions of years, leaving behind the dry, cold, frozen desert we see today. Here on Earth, our living magnetic field also gives rise to one of nature's most spectacular displays. The auroras, the northern and southern lights, those soft, glowing curtains of green and purple light that dance near the poles, are not just a beautiful sight. They are proof of our planet's protection. They are the visible result of charged solar particles interacting with the Earth's magnetic field lines. The light is born where our shield bends and deflects the storm. It is a beautiful reminder that our planet's rotation still powers an invisible force field around us, a silent guardian for all of life. But the spin's influence does not stop at shielding and sunlight. It also governs the very air we breathe, the atmosphere itself. Because the Earth is a turning sphere, any object moving over its surface, like a current of air or water, gets deflected. This phenomenon is known as the Coriolis effect. It is a subtle but powerful force that creates the vast, spiraling systems of winds and ocean currents that define our global weather patterns. It is the reason why hurricanes and typhoons spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It is why the jet streams, those high-altitude rivers of air, flow in predictable paths around the globe. And it is why the great ocean gyres carry warm water from the equator towards the poles and cold water back again, regulating the planet's climate. Without the Coriolis effect, our weather patterns would collapse into chaos. Organized storms would not form, and the climate would not be able to balance itself. The rotational speed of a planet, it turns out, directly shapes its climate. NASA's Global Modeling and Assimilation Office has run powerful computer simulations of exoplanets with different rotation speeds. A very slow rotation causes one side to overheat and the other to freeze, just as we imagined. A much faster rotation can generate extreme, planet-scouring winds and short, disruptive days that prevent atmospheric stability. The Earth's 24-hour rhythm appears to be almost perfect. It is long enough to distribute the sun's energy evenly, but short enough to prevent any one side from overheating. It is a cosmic sweet spot. The length of the day also has a profound effect on biology itself. Over billions of years of evolution, living organisms have developed internal clocks, known as circadian rhythms, that are precisely aligned with the planet's 24-hour rotation. According to a vast body of research published by institutions like the National Center for Biotechnology Information, almost every living cell on Earth, from the simplest bacterium to the neurons in your brain, carries a molecular timekeeper that is synchronized to this daily cycle. This internal rhythm regulates when plants open their leaves to photosynthesize, when nocturnal animals begin to hunt, when migratory birds know it is time to travel, and even when humans feel sleepy or awake. If the Earth were to suddenly stop rotating, this deep biological harmony would shatter. The reliable cycle of light and dark would be gone, and life as we know it could not adapt. Rotation also played a crucial role in how the moon became our constant companion in the night sky. Billions of years ago, when the Earth was still young and molten, it is believed that a Mars-sized object, which scientists have named Theia, collided with our planet. The cataclysmic impact sent a vast cloud of debris into orbit, which later coalesced under gravity to form the moon. This giant impact also dramatically increased the Earth's spin, giving it a much shorter day than it has now. Over the eons, the moon's gravity has been gently pulling on the Earth, acting as a brake and gradually slowing down our spin. This tidal interaction has lengthened our days from perhaps as little as 6 hours in the very beginning to the comfortable 24-hour cycle we have now. At the same time, these tidal forces between the Earth and the moon have kept our planet's axial tilt remarkably stable. This stability is what gives us our regular seasons and prevents extreme, catastrophic climate swings. Data from the European Space Agency's Gaia mission, which maps the stars with incredible precision, confirms that this kind of axial stability is likely essential for the long-term habitability of a planet. Worlds that wobble too much on their axis often experience wild and unpredictable climate variations that would be hostile to life. The Earth and the Moon now exist in a slow, graceful, gravitational embrace. The same tides that shape our oceans are also slowing our rotation by about 1.7 milliseconds every century, a measurement confirmed with incredible accuracy by NASA's Jet Propulsion Laboratory, using lasers bounced off reflectors left on the Moon by the Apollo astronauts. It is a profound reminder that even the length of our day, the very heartbeat of our world, is not a constant. It is gradually, imperceptibly changing, one moment at a time. If we look beyond our own planet, we find that rotation plays a similarly crucial role in shaping other worlds. Jupiter, the giant of our solar system, spins once every 9 hours and 56 minutes, making it the fastest rotating planet. Its incredible speed drives ferocious jet streams and colossal storms, including the Great Red Spot, a hurricane larger than the entire Earth that has been raging for centuries. On Jupiter, Rotation creates chaos, yet it also creates a form of stability, distributing heat from its interior and shaping the planet's beautiful, banded cloud patterns. Meanwhile, Venus, which rotates backward and extremely slowly, one full rotation takes 243 Earth days, has almost no magnetic field. Its thick, toxic atmosphere of carbon dioxide has trapped heat in a runaway greenhouse effect, making it the hottest planet in the solar system, with surface temperatures hot enough to melt lead. The comparison is striking. Too fast, and a world is dominated by storms. Too slow, and its protective shield disappears, its climate spiraling out of control. Even Mars, with a day just 40 minutes longer than our own, shows what happens when a planet's internal motion fades. As its core cooled and solidified, its once strong magnetic field vanished, allowing solar radiation to strip away most of its air and water. Faint remnants of magnetism still linger in the planet's crust, like ghostly traces of a spin that once sustained a more dynamic and possibly living world. Rotation, then, is not an optional extra for a habitable planet. It is fundamental. In the year 2023, scientists using the James Webb Space Telescope observed the atmospheres of distant exoplanets like WASP-39b and TRAPPIST-1e. They are discovering that those worlds with measurable spin and atmospheric circulation show clearer signs of chemical balance and more even temperature distribution. Without rotation, a planet's energy remains trapped on one side or lost from the other, creating violently unstable environments. As NASA's exoplanet exploration program summarizes, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation may also be tied to the longevity of magnetic protection on these distant worlds. A study published in 2021 by the Harvard-Smithsonian Center for Astrophysics noted that exoplanets with rapid spins tend to maintain their molten metallic cores for longer periods of time, thus extending the life of their protective magnetic fields. These fields, in turn, shield the planet's atmosphere from its star's radiation and may significantly increase the likelihood of surface liquid water, which we believe is the essential ingredient for life. So when we ask, did spinning make life possible? The overwhelming body of evidence whispers a quiet but firm yes. Rotation shapes everything from a planet's day length and its temperature gradients, to its atmosphere, its weather, and its magnetic safety. Life, it seems, does not thrive in spite of motion, but because of it. Our world's rotation speed has changed over the eons, yet its effects continue to echo across time. It controls the rhythm of the tides, the growth of the forests, the great migrations of animals. It defines our very sense of time itself, not as an abstract idea, but as the physical, tangible turning of the world beneath our feet. As the astrophysicist Neil deGrasse Tyson once said, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Take a moment to feel that turn, to listen to it with more than your ears. Every rotation of our planet carries the whisper of 4.5 billion years of balance and motion. If the Earth stopped spinning tomorrow, the oceans would surge towards the poles in a global tsunami. The atmosphere would collapse into chaos, and our planet would lose its breath. But tonight, as it spins gently, silently beneath you, everything still works, perfectly, quietly, continuously. So perhaps it is no exaggeration to say that the rotation of the Earth is the quiet, unseen architect of life. The same cosmic motion that once swirled dust and gas into a planet now spins that planet into morning, into wind, into rain, into you. Now, as we drift deeper into this cosmic journey, let us follow that principle of rotation outward, to the very edges of physical law, to where spinning no longer just shapes life, but begins to bend something even stranger, even more fundamental. Because when rotation is pushed to its absolute limit, it does not just move matter, it can start to twist the very fabric of time itself. And that is where our next chapter begins. When rotation reaches its ultimate limit, it ceases to be mere motion and becomes a form of distortion, at the most extreme speeds and densities imaginable, turning objects no longer just move through space. They begin to pull and drag at the fabric of space-time itself. The great physicist Albert Einstein, in his General Theory of Relativity published in the year 1915, predicted that gravity and motion are inseparable. They are two expressions of the same fundamental truth, that mass and energy curve the geometry of space-time. The greater the mass, the greater the energy, or the faster the spin of an object, the more it twists the very geometry of the universe around it. This twisting of space-time by a rotating object is known as frame dragging, or the Lense-Thirring effect. It is one of the most subtle, beautiful, and now verified predictions of modern physics. Imagine space-time as the surface of a calm, deep lake. A non-moving, massive object like a stationary planet would create a simple depression in that surface, like a heavy ball resting on a rubber sheet. But when a massive object spins, like our Earth or, more dramatically, a black hole, it does more than just create a depression. It begins to stir that lake, creating tiny, invisible vortices in the very flow of space and time. In those cosmic whirlpools, the direction of time itself can begin to curve. The NASA physicist Francis Everett, who led the landmark Gravity Probe B experiment, once described it with a wonderful analogy. He said, "As the Earth rotates, it drags space-time around with it, much like a spinning sphere would twist the honey in which it is immersed." The Gravity Probe B mission, launched in the year 2004, was one of the most technologically sophisticated experiments ever attempted. It used 4 of the most perfectly spherical objects ever created by humanity, gyroscopes made of fused quartz and niobium, so smooth that if they were scaled up to the size of the Earth, the tallest mountain would be only a few feet high. These ultra-precise gyroscopes were placed in a polar orbit 400 miles above the Earth. Their job was to measure, with almost unbelievable precision, whether the space-time around our planet was indeed being twisted by its rotation. After a year of painstaking observation and years more of data analysis, NASA confirmed the effect. Our planet's gentle rotation does indeed drag the fabric of space-time. The effect is minuscule, twisting space-time by about 1/100th of an arc-second per year, an angle so small it is like measuring the thickness of a human hair from a quarter of a mile away. That may sound insignificant, but it matched Einstein's equations with extraordinary precision. Even our gentle planet, spinning just once every 24 hours, is capable of bending the flow of time. Now, imagine a rotation, not once a day, but hundreds of times a second. And imagine a gravitational field not just strong, but billions of times stronger than Earth's. That is what happens in the vicinity of a neutron star. When a truly massive star exhausts its nuclear fuel, it collapses under its own immense gravity. The collapse is so violent that it squeezes matter to a density beyond our comprehension. Protons and electrons are forced to merge, forming a sea of neutrons. The result is an object only about 12 miles wide, a city-sized sphere, but with a mass greater than that of our entire Sun. To conserve its angular momentum from its former life as a giant star, these collapsed objects spin at unimaginable speeds up to 700 times per second. Astronomers call these rapidly spinning neutron stars pulsars, because their powerful magnetic poles emit beams of radiation that sweep across space like the beam of a cosmic lighthouse. As they rotate, they create the strongest known magnetic fields in the universe, and they twist space-time so violently that even light struggles to travel in a straight line near them. NASA's Neutron Star Interior Composition Explorer, or NISA, an instrument mounted on the International Space Station, has mapped these distortions around pulsars. Its data shows that time near a pulsar ticks more slowly than it does on Earth. The stronger the spin and the more intense the gravity, the slower the clock. Einstein's equations tell us that this is not magic. It is a real physical effect called gravitational time dilation. Time, he showed, is not absolute. It runs more slowly in regions of stronger gravity or for objects moving at higher speeds. When you are close to a massive spinning body, space-time itself is being pulled into its rotation. You cannot stay still relative to the rest of the universe. You are dragged along, as if the universe itself is rotating you. This phenomenon becomes most extreme near a Kerr black hole, which is the scientific name for a black hole that spins. Named after the brilliant mathematician Roy Kerr, who first solved Einstein's complex equations for a rotating black hole in 1963. A Kerr black hole is perhaps the most exotic and mind-bending structure we know of in the cosmos. Unlike a simple, non-rotating black hole, which merely pulls everything inward towards its central singularity, a Kerr black hole spins space-time around its axis of rotation. Close to its event horizon, the point of no return, the speed of this space-time rotation approaches the speed of light. In this region, nothing, not even time itself, can resist being dragged along. The region just outside the event horizon, where this frame-dragging effect is inescapable, is called the ergosphere. Within the ergosphere, nothing can remain stationary relative to the distant stars. Every particle, every photon of light must rotate with the black hole. It is as if space itself has become a liquid, spinning in a vast, invisible, and unstoppable whirlpool. In the year 2021, using data from NASA's Chandra X-ray Observatory, scientists observed matter spiraling around the supermassive black hole at the center of the galaxy M87. They were able to confirm that it is rotating at a speed near the absolute limit predicted by the theory of relativity. Inside that cosmic whirlpool, time behaves in ways that defy our everyday intuition. If you could somehow hover safely near the ergosphere, an impossible feat, for now your clock would tick at a dramatically slower rate than the clocks of those back on Earth. For every single minute you experienced in that warped region of space-time, hours, years, or even centuries could pass for the rest of the universe. Einstein called this the warping of time, a direct and inevitable consequence of motion and gravity acting together. As he once wrote, time and space are modes by which we think, not conditions in which we live. The European Space Agency's Event Horizon Telescope, a global network of radio telescopes working in unison, captured the first ever image of a black hole's shadow in the year 2019, and later, in 2022, released the image of Sagittarius A*, the supermassive black hole at the heart of our own Milky Way galaxy. The luminous, glowing ring that we see in these images is not light coming from the black hole itself, but from superheated matter spiraling around it. The light is bent, distorted, and delayed by the extreme curvature of space-time. Those glowing arcs are direct, visual proof that rotation and gravity, when combined, can bend not just the path of light, but the very flow of time. These same laws of relativity apply on smaller, more familiar scales as well. Even the satellites that orbit our own Earth experience tiny but measurable differences in the flow of time. The Global Positioning System, or GPS, that many of us use every day, must constantly correct for the effects of both gravitational time dilation, because the satellites are in a weaker gravitational field than we are on the surface, and velocity-induced time dilation, because they are moving so fast. If these relativistic effects were not accounted for, the atomic clocks on board the GPS satellites would drift by about 38 microseconds every day. That tiny difference would be enough to cause navigation errors of several miles to accumulate, making the system useless. So even here, in our daily lives, where space-time seems perfectly calm and flat, the bending of time is not just a strange theory, it is a practical, engineering reality. When astrophysicists run computer simulations of the regions near a Kerr black hole, the mathematics becomes truly breathtaking. The The rotation can twist space-time so sharply that strange theoretical possibilities emerge, such as closed time-like curves. These are paths in space-time where a particle could, in theory, loop back and arrive at an earlier point in its own timeline. Whether these time loops are physically real or just a mathematical artifact of the equations remains highly uncertain, but they emerge naturally from Einstein's description of a rotating universe. In these extreme environments, the fixed, linear concepts of past, present, and future begin to lose their meaning. The James Webb Space Telescope, with its incredible infrared precision, is now observing the accretion disks of distant quasars, extremely bright galaxies, powered by supermassive, rapidly rotating black holes in the early universe. The spectra of light from these disks, when analyzed by scientists, show that the light has been stretched and redshifted, a clear sign that time is running more slowly in those intensely gravitational, rapidly rotating regions. Some of the light we are detecting today left those spinning giants over 13 billion years ago, meaning we are watching time itself being stretched across the vastness of the cosmos. Rotation, it turns out, does not just shape matter. It defines how time flows in its vicinity. The faster the spin and the denser the object, the greater the warping of space-time. From our own gentle planet to the violent, chaotic hearts of distant galaxies, the universe uses spin to sculpt both motion and time. What we call now is different everywhere, depending on how fast and how deep the local space-time is turning. Even light, which normally travels at the universe's ultimate speed limit, is forced to bend and slow down as it passes near rotating masses. NASA's New Star and the European Space Agency's XMM Newton missions have captured X-ray echoes from around black holes. These are photons of light that have been briefly trapped in the rotating space-time, spiraling around the black hole before managing to escape. In these echoes, we can see time being stretched like a soft thread, a measurable, predictable, yet endlessly strange effect. One might wonder, then, whether the universe itself is twisting time on the grandest scale of all. If the entire cosmos has a slight rotation, as some evidence suggests, it could subtly influence the way time flows across billions of light-years. While the current cosmological data from the European Space Agency's Planck satellite shows no strong evidence for such a universal spin, the question remains tantalizingly open. Even the faintest twist, spread over cosmic distances, might leave its fingerprints in the polarization of ancient light, faint hints that time itself has a preferred, universal direction. As the physicist Kip Thorne, a Nobel laureate and a co-author of the book, The Science of Interstellar, explained, in the warped space-time near a spinning black hole, the future of one observer can become the past of another. Rotation does not just bend trajectories. It can bend the very sequence of events, the fundamental rhythm of existence. And yet, for all its strangeness, this effect is consistent and measurable. The dilation of time around rotating bodies has been verified with incredible accuracy by atomic clocks aboard aircraft, satellites, and in laboratories at different altitudes. The faster you move, or the deeper you fall into a gravitational well, the slower your time flows relative to others. It is not an illusion. It is the universe keeping its books perfectly balanced. So yes, rotation can and does bend time. But what is even more intriguing is why that bending seems to follow such a perfect, predictable pattern, a smooth and universal law that links motion, gravity, and energy into one seamless continuum. From Einstein's elegant equations to every single ticking satellite orbiting our planet, it all points to one profound truth. The universe does not just move through time. It creates time through its motion. Take a slow, deep breath. Right now, your own personal sense of time is tied to the Earth's gentle spin, to the sun's immense pull, to the silent turn of the galaxy. You are surrounded by, and part of, a motion so precise and so grand that it writes the very seconds you live in. And if rotation can bend and control time, a new question begins to surface. What happens when we look at this relationship in reverse? When time itself seems to control the spin? This is the mystery waiting in our next chapter, a quiet inquiry into the clockwork of the cosmos. If spin controls time, who or what controls the spin? Every single second that you live is shaped and defined by motion. The ticking of a watch on your wrist, the digital pulse of an atomic clock, even the steady, rhythmic beat of your own heart, all of these are dependent on something, somewhere, spinning. At the most fundamental level, electrons rotate within their atomic orbitals. On a planetary scale, the Earth turns once every 24 hours, and as we have learned, as it spins, it drags the fabric of space-time just enough to change the very flow of time. A clock placed at the equator, where the Earth's surface is moving fastest at about 1,037 miles per hour, will run ever so slightly slower than a clock placed at the North or South Pole. This is not because of differences in temperature or air pressure. It is a direct consequence of Einstein's theory of relativity. His work showed that motion and gravity can stretch or compress time, depending on how fast you are moving and how deep you are within a gravitational field. So yes, in a very real and measurable way, spin controls time. But this leaves us with a deeper, more profound question. Who or what controls the spin itself? To begin to answer this, scientists look to the most reliable and precise keepers of time that humanity has ever built: atomic clocks. Inside these incredible devices, atoms of a specific element, usually cesium, are held in a vacuum chamber. The electrons within these atoms whirl around the atomic nuclei at very specific, fixed energy levels. When these electrons are stimulated with microwave radiation of a very precise frequency, they will jump from one energy level to another. When they fall back down, they release a photon of light at an exact, unwavering frequency. That frequency, as defined by the cesium-133 atom, is what sets the official length of 1 second. By international agreement, 1 second is defined as the duration of 9,192,631,770 cycles of the radiation that corresponds to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Those carefully chosen words, printed by the International Bureau of Weights and Measures, describe how every single second of your life is calibrated to the tiny, quantum spin of electrons inside an atom. The rotation of electrons is not a physical twirling like a spinning top, but a fundamental, intrinsic property of matter known as quantum spin. In the strange world of quantum mechanics, particles like electrons carry discrete spin values that determine how they behave in magnetic fields, how they form chemical bonds, and even how they obey the Pauli exclusion principle, the fundamental rule that states that no two electrons can occupy the exact same quantum state at the same time. So, at its very smallest and most precise scale, our measurement of time is completely dependent on quantum spin. It is not the turning of a planet that defines our most accurate second, but the internal, angular momentum of atoms themselves. But just as these atomic spins govern time inside our laboratories, the grander spins of planets and stars govern time on a cosmic level. The Earth's rotation, as we know, defines the length of a day, while its stately orbit around the Sun defines the length of a year. These cosmic motions, however, are not perfectly fixed. They slowly drift over time. The tidal forces from the Moon's gravity are gradually slowing down the Earth's spin, adding about 1.7 milliseconds per century to the length of each day. To keep our highly precise atomic time synchronized with the slightly wobbly, gradually slowing planetary time of the Earth, scientists have implemented a system called leap seconds. Occasionally, the world's official atomic clocks are adjusted by 1 single second to bring them back into alignment with the planet's natural rotation. In a very real sense, we are constantly recalibrating human time to match the Earth's ancient, cosmic spin. If you were to compare two of these hyper-accurate atomic clocks at different latitudes on Earth, you would find measurable differences in the rate at which they tick. A clock placed at sea level near the equator, which is moving fastest due to the Earth's spin, runs slightly slower than a clock placed high in the mountains or near one of the poles. This is a combined effect of both special relativity, due to the difference in speed, and general relativity, due to the difference in gravitational potential. As NASA explains, a clock on the equator ticks more slowly than one at the poles because it is moving faster and is slightly deeper in the Earth's gravitational potential. Well, because the Earth bulges at the equator. The difference is tiny, just a few nanoseconds per day, but it is real and it is measurable. Your phone's GPS system must correct for this effect constantly. Each of the 24 GPS satellites orbits the Earth at about 8,700 miles per hour, from an altitude of about 12,500 miles above the surface. In their high orbit, they experience weaker gravity and are moving at a very high speed, both of which cause their onboard atomic clocks to run faster than clocks on the ground by about 38 microseconds every single day. If this relativistic drift were not corrected, it would cause navigational errors of several miles to accumulate every few hours, making the entire system useless. To keep time consistent across the network, engineers have to combine Einstein's elegant equations with real-world measurements, literally adjusting for the curvature of space-time caused by the Earth's mass and rotation. So, every single time you check a map on your phone or receive a location signal, you are witnessing relativity in action. It is a quiet, ongoing collaboration between gravity, motion, and spin. But this brings us back to the original question: who started all this spinning in the first place? Astronomers trace the origin of spin back to a fundamental conserved quantity in physics: angular momentum. When our solar system formed about 4.6 billion years ago, it began as a vast, slowly rotating cloud of gas and dust. As this cloud began to collapse under its own gravity, it started to spin faster and faster, just like that figure, skater pulling in her arms. That primordial motion, that original spin, distributed angular momentum to everything that formed within the cloud. The sun, the planets, their moons, each body still carries a portion of that ancient, initial rotation. There is no external force that is continually pushing them to keep them spinning. They continue to spin because of inertia, the same law that dictates that an object in motion will stay in motion until something resists it. In the near-perfect vacuum of space, where there is almost no friction, these cosmic spins can last for billions upon billions of years. So, the simplest and most profound answer to the question, who controls the spin, is this: no one. The universe does not need a hand to keep it turning. Once it was set in motion, it continues on its own accord. But the relationship between spin and time grows ever stranger and more intricate the deeper we look. Inside atoms, quantum spin determines the energy states of electrons, which we use to define our most precise second. On planetary scales, the physical spin of the Earth defines our day. On cosmic scales, the spin of massive objects drags and twists time itself. And all of these different levels, from the quantum to the cosmic, are connected by one single, unbreakable law. Angular momentum is conserved. Time, in this sense, is not some independent, absolute entity that flows on its own. It is a reflection, a measurement, of how energy and spin interact. In 2016, the European Space Agency's Gaia mission began to map the precise motions and positions of over 1 billion stars in our Milky Way galaxy. The data it has collected has revealed that our entire galaxy is rotating, completing one full revolution every 230 million years, carrying the Sun and all its planets along with it in a vast, silent spiral. Each star's orbit contributes to a grand cosmic timepiece. One rotation of the galaxy marks the passage of a galactic year, a rhythm of cosmic time. Just as atomic spin defines our seconds, stellar spin defines the eons. Even our own sun spins, rotating once every 27 days at its equator. But it does not spin as a solid body. Its poles rotate more slowly than its equator, a phenomenon called differential rotation. This twisting, shearing motion of the sun's plasma generates its incredibly complex and powerful magnetic fields. These fields are what shape solar flares and coronal mass ejections. When these magnetic storms erupt from the sun and travel to Earth, they can distort our own magnetic field, creating beautiful auroras, but also posing a risk to our satellites and power grids. So, from the atomic scale to the solar scale, spin is not a passive property. It actively sculpts magnetic fields, it defines natural rhythms, and it interacts with the very tools we use to measure time. Einstein's theory of relativity linked all of these patterns together in a single, beautiful, mathematical framework. In his equations, the geometry of space-time is determined by the distribution of energy and momentum, and this explicitly includes angular momentum. In other words, spin curves time. If you could somehow remove all the spin from the universe, space-time would become simpler, flatter, less dynamic. But when you add spin, it warps, gently for planets like ours, and violently for objects like black holes. We might then say that time itself is recorded in motion. The second is written in the language of atomic spin. The day is written in the language of planetary spin. The cosmic epoch is written in the language of galactic spin. Everything that moves, measures. And everything that measures, moves. In 2022, the James Webb Space Telescope observed some of the most distant galaxies ever seen, whose light has been traveling for over 13 billion years to reach us. And even in those primordial, infant galaxies, astronomers have detected organized rotation. This is a clear sign that angular momentum existed almost immediately after the Big Bang. It means that the fundamental law connecting spin and time has been in operation since the universe's earliest seconds. Spin is not a product of time. It is part of what gives time its flow, its direction, its very meaning. So, if spin governs time, and spin itself arises naturally from the conservation of motion that was present at the very beginning, then who, or what, controls it all? The most precise and honest answer that science can currently offer is that the universe controls itself. It is a self-regulating system. Every spin is balanced by another. Every slowing motion is matched by an equal and opposite exchange of momentum somewhere else. Even the smallest quantum particle, in its strange and probabilistic dance, obeys these same fundamental conservation laws, ensuring that the total amount of angular momentum in the universe remains perfectly conserved across all of space and all of time. The scientists at NASA's Jet Propulsion Laboratory put it in simple and elegant terms. The laws of motion do not change. The universe runs on balance. What is lost in one place is gained in another. There is no master clockmaker, no hidden hand turning the gears. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope. It is its built-in, fundamental way of keeping everything aligned and in balance. From the atoms that make up your body to the stars that shine in the sky above, the same elegant principle governs every single scale of existence. Even when systems decay, or collide, or slow down, their angular momentum is not lost. It is transferred onward, keeping the great cosmic clock ticking. And so, when you ask, who controls the spin, the universe, gently, silently, answers, no one must. Motion is self-sustaining. It is the quiet, perfect balance that underlies both time and existence itself. Take a slow breath. The atoms within you are spinning in harmony with the turning Earth, the orbiting moon, and the spiraling galaxy. You are already a part of that ancient, conserved motion. Every heartbeat you feel is a fraction of a universal rhythm that began long before there were clocks, or calendars, or even light itself. And as that rhythm continues, another, deeper question slowly begins to rise. A question that stretches beyond the nature of motion and into the very structure of the cosmos itself. If the universe depends on such a perfect and delicate balance, what happens when that symmetry breaks? For it is in that breaking, that first imperfection, that the universe as we know it may have truly begun. That is where we drift next. If everything in the beginning had been perfectly, flawlessly balanced, nothing would ever have moved. Imagine a universe born in a state of absolute equilibrium, every point in space identical to every other, every particle perfectly matched by an antiparticle, every force pushing with the exact same strength as the force pulling. In such a universe, there would be no reason for change. There would be no stars, no atoms, no time, only a profound and eternal stillness, unchanging and featureless. But the universe we know, the one we inhabit, began not with perfection, but with a tiny, crucial imperfection, a small crack in the mirror of symmetry that allowed everything we see and everything we are to unfold. In the language of physics, symmetry means that the laws of nature behave in the exact same way, regardless of your location, your direction, or your perspective. When symmetry holds perfectly, nothing has a reason to change. But when that symmetry breaks, even slightly, motion appears, structure emerges, and time gains a direction. As the scientists at NASA's Goddard Space Flight Center have described it, the universe exists as we know it because perfect symmetry did not last. Let us drift back again in our minds to those first incomprehensible fractions of a second after the Big Bang. According to the standard model of particle physics, the early universe was a hot, dense plasma, a soup of fundamental particles and energy, where the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were once unified into a single, elegant superforce. But as the universe expanded and cooled with incredible rapidity, these forces began to separate from one another. This process, known to physicists as spontaneous symmetry breaking, shaped everything that followed, from the structure of the atoms in your body to the very fabric of space-time itself. The European Space Agency's Planck mission mapped the cosmic microwave background, that faint afterglow of the Big Bang, and found that it was astonishingly uniform. Yet, as we discovered, it was not perfect. There were tiny variations in temperature, only 1 part in 100,000, that reveal the first tangible signs of this broken symmetry. Those minute differences in energy density, those tiny imperfections in the otherwise smooth fabric of the early universe, later acted as seeds. Gravity, over billions of years, pulled more matter towards these slightly denser regions, and they grew into the vast clusters of galaxies, the individual stars, and the planets that we see today. Without those initial fluctuations, the universe would have remained a smooth, static, and featureless mist, an endless and eternal fog with no structure at all. Even the existence of matter itself, the very substance of our world, owes its existence to a broken symmetry. In the incredibly hot and energetic early universe, energy was constantly converting into pairs of matter and antimatter particles. But theory suggests that for this process to result in the universe we see, there must have been a slight imbalance. For every 1 billion particles of antimatter created, there must have been 1,000,000,001 particles of matter. This slight, almost imperceptible asymmetry, known as baryon asymmetry, is the reason we exist. When the universe cooled, the matter and antimatter particles annihilated each other in a flash of energy. But because of that initial imbalance, a tiny fraction of matter was left over. That leftover matter, the surviving one in a billion, became the building blocks for the stars, the planets, and everything we can see and touch today. In the year 1964, the physicists James Cronin and Val Fitch discovered the first experimental evidence of this subtle asymmetry in the behavior of subatomic particles. Their experiments with particles called neutral kaons showed that the laws of physics do not treat matter and antimatter in a perfectly symmetrical way. This effect is now called CP violation. Their discovery, which earned them the Nobel Prize in Physics, provided the first crucial clue that the universe has a fundamental preference for one type of substance over its mirror image. It prefers matter. As the Particle Physics Division at the European Space Agency notes, without this CP violation, the universe today would contain no matter at all, only a diffuse bath of light. So, in a very real sense, it was an imperfection, a flaw in the symmetry, that made everything possible. The exact mechanism behind this universe-creating imbalance is still one of the biggest mysteries in physics. At CERN, the European Organization for Nuclear Research, the Large Hadron Collider smashes particles together at nearly the speed of light to recreate the conditions of the early universe and study particles like the Higgs boson. The Higgs boson plays a crucial role in another key example of symmetry breaking, known as electroweak symmetry breaking. When the universe was extremely hot, the electromagnetic force and the weak nuclear force were one and the same. But as the universe cooled below a critical temperature, about 10 to the power of -12 seconds after the Big Bang, the Higgs field, which permeates all of space, froze into a non-zero value. This event gave fundamental particles their mass and broke the symmetry between light and matter. It is often said that the Higgs field is what locked the universe into its current form, creating the fundamental differences between particles that allowed for complexity to arise. But not all symmetry breaking is violent or happens on a quantum scale. Sometimes it is gentle, almost poetic. Imagine again that perfectly balanced pencil, standing on its tip. It will eventually fall. The laws of physics do not dictate which direction it must fall in, but it must choose one. The universe may have chosen a direction for time in a similar way. In the very first instant, time could have flowed equally forward or backward, but a tiny, random fluctuation, perhaps in entropy, the measure of disorder, or perhaps in quantum probability, pushed it in the forward direction, setting the inexorable arrow of time that we experience. As the physicist Sean Carroll once wrote, the arrow of time is the result of a low entropy, highly ordered state at the beginning of the universe, a state of broken symmetry that all later moments remember. So, when we measure the passage of time, we are really measuring how far the universe has drifted from its initial, perfectly ordered, but ultimately unstable, state of symmetry. Even the beautiful, web-like structure of the cosmos on the largest scales, the vast filaments of galaxies and dark matter that connect galaxy clusters, arises from this initial imbalance. The James Webb Space Telescope's deep field images show galaxies forming along these invisible threads of dark matter, which in turn trace the patterns of the earliest quantum fluctuations in density. Those fluctuations began as random, microscopic variations that were magnified to astronomical scales by the process of cosmic inflation just moments after the Big Bang. What began as tiny, random irregularities became the grand architecture of the universe. Without asymmetry, even gravity itself could not work the way it does. A perfectly uniform distribution of matter would pull equally in all directions at once, resulting in no net force and no motion. But with slight unevenness, gravity could take hold, drawing matter into clumps, forming the first protogalaxies, stars, and eventually, planets. NASA's WMAP mission described this principle with beautiful simplicity. If the early universe had been perfectly smooth, no structure could have formed. No galaxies, no stars, no life. Even at the deepest quantum level, fundamental particles betray this same fundamental imbalance. Neutrinos, for instance, are known to have a property called chirality. They all appear to spin in the same left-handed direction relative to their motion. This handedness of the universe may be another ancient echo of the original symmetry-breaking event. It is a pattern that repeats itself from the tiniest of scales to the largest, from the spin of subatomic particles to the rotation of entire galaxies. Everywhere we look, the universe shows a subtle preference. Galaxies appear to rotate clockwise or counterclockwise in slightly unequal numbers. And perhaps most mysteriously of all, the very molecules of life on Earth, amino acids and sugars, also have a handedness. This biological bias, called homochirality, underlies all of biology as we know it. Though life arose on Earth billions of years after the Big Bang, its fundamental chemistry still seems to reflect the same ancient asymmetry that was written into the very fabric of the cosmos at its birth. This profound connection between a cosmic imbalance and the structure of life has fascinated scientists for decades. A study from the year 2020 by NASA's Astrobiology Institute suggested a possible mechanism. Intense, polarized ultraviolet light from young, massive stars in the early galaxy may have preferentially destroyed right-handed amino acids, leaving a surplus of left-handed ones to seed the building blocks of life on planets like Earth. If this is true, then even the fundamental spin of life's molecules owes its direction to the universe's first broken symmetry. But perhaps the most elegant and sought-after evidence for this principle lies hidden within the polarization of the cosmic microwave background itself. The Planck satellite detected tiny swirling patterns in the polarization of this ancient light, known as B-mode polarization, which may be the faint fingerprints of primordial gravitational waves. These waves would be the ripples in space-time generated by cosmic inflation, the universe's first and fastest expansion, the very moment when perfect symmetry gave way to violent motion. If these B-mode signals are confirmed, they would be direct evidence that the universe's very first act was to break a perfect balance. From the way light bends around massive objects to the way galaxies align in vast cosmic structures, everything we can measure points back to that single, powerful principle. Imperfection drives creation. Symmetry is elegant, but it is also sterile and fragile. Break it, even slightly, and the universe wakes up. As the theoretical physicist and Nobel laureate Murray Gell-Mann once said, "If the world were perfectly symmetrical, there would be nothing. It is the deviations, the slight differences in energy, in motion, in charge, that make reality possible." When we observe the universe through our powerful telescopes like the James Webb, what we are really seeing is the fossil record of broken symmetry. We are witnessing the echoes of the first flicker of imbalance that eventually became time, structure, and light. And from that faint, initial imperfection, everything else followed: galaxies, planets, oceans, and the quiet, rotating world beneath your feet. Take a slow, deep breath. You yourself are living proof of asymmetry. You are a being made from matter that once outnumbered its mirror twin, antimatter, by just 1 part in a billion. Every single atom in your body carries the indelible trace of that ancient cosmic bias, a preference that has been preserved since the first microseconds of existence. So yes, the universe as we know it began because symmetry broke. Perfection gave way to motion, and motion gave rise to time. A small, essential crack in the balance of the void created everything that would ever spin, or shine, or breathe. And as we follow the consequences of that first imbalance outward through cosmic history, we reach a new puzzle. A question not about beginnings, but about what keeps the cosmos together, despite its restless, eternal motion. Because if the galaxies we see are spinning faster than our laws of gravity say they should, then something invisible, something powerful, must be holding them in place. And from that apparent imbalance, a new mystery begins to turn, one hidden in the profound darkness between the galaxies. Galaxies spin at impossible speeds. The stars on their outer edges, far from the gravitational anchor of the central core, move so fast that by all the known laws of physics, they should fly off into the intergalactic void. They should be scattered like glowing sparks flung from a rapidly turning wheel. And yet, they are not. They remain in their orbits, held in a graceful, stable dance. Something unseen, something vast and massive, is holding them in place. A silent, invisible mass that outweighs everything we can see, all the stars, all the gas, all the dust, by a factor of 5 to 1. Astronomers call this mysterious substance dark matter. It does not shine, it does not reflect, and it does not absorb light. It does not collide, or melt, or form into atoms. It is utterly invisible to all our telescopes. But it has gravity, it pulls. And that immense, invisible pull is what keeps entire galaxies from tearing themselves apart. This profound mystery began to unfold in the 1930s, when the brilliant and eccentric Swiss astrophysicist Fritz Zwicky was studying the Coma Cluster, a vast collection of more than 1,000 galaxies drifting through space, some 320 million light-years away. Zwicky carefully measured the speeds at which the individual galaxies within the cluster were moving. He found that they were moving so fast that the visible mass of the cluster, all the stars and gas he could see, was not nearly enough to gravitationally bind them together. The cluster should have flung itself apart billions of years ago. He proposed something shocking, something that most of his colleagues at the time dismissed. There must be an enormous amount of unseen mass within the cluster, providing the missing gravity needed to hold it together. He called this missing mass Dunkle Materie, which is German for dark matter. For decades, Zwicky's idea remained a fringe curiosity, a whisper in the halls of astronomy. That is, until the 1970s, when the pioneering American astronomer Vera Rubin began her meticulous work measuring the rotation curves of spiral galaxies. Using data from the Kitt Peak National Observatory in Arizona, she measured the orbital speeds of stars at various distances from the centers of galaxies like our neighbor, Andromeda. What she found was revolutionary, and it changed our understanding of the cosmos forever. According to Newtonian physics and our understanding of gravity, the orbital speeds of stars should decrease the farther they are from the galactic center, just as the outer planets in our solar system, like Neptune, move much more slowly than the inner planets, like Mercury. But Rubin's graphs were not what anyone expected. They were flat. The stars far from the galactic centers were orbiting just as fast as the stars near the core. It was a discovery that defied all conventional logic. There had to be something unseen, providing extra gravity throughout the entire galaxy, even in its vast, empty-looking outer regions. As NASA later summarized her groundbreaking work, the rotation curves of galaxies tell us that there is much more mass than meets the eye. That unseen mass, dark matter, now appears to make up about 85% of all the matter in the universe. It is roughly 5 times more abundant than the ordinary, baryonic matter that makes up you, me, the stars, the planets, and everything we have ever seen or touched. Scientists now believe that galaxies like ours sit inside vast, spherical halos of dark matter. These invisible halos extend far beyond the visible edges of the galaxies themselves. Each halo acts as a kind of cosmic scaffolding, a gravitational framework that binds the stars and gas together. Without this dark matter halo, our own Milky Way galaxy would unravel and dissipate in just a few million years. Sophisticated computer simulations from places like NASA's Goddard Space Flight Center show that dark matter provides the essential cosmic glue that allows galaxies to form in the first place, to merge with each other, and to persist for billions of years. The European Space Agency has also observed the effects of this invisible structure through a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time. When light from a very distant galaxy passes near a massive galaxy cluster filled with dark matter, the unseen mass of the cluster warps space-time so much that it acts like a giant lens, bending, magnifying, and distorting the background light into beautiful, graceful arcs and rings. The European Space Agency's Euclid mission, launched in the year 2023, is designed specifically to map this lensing effect across billions of galaxies, with the goal of creating the most detailed, three-dimensional chart of the distribution of dark matter ever made. Even before Euclid, the Hubble Space Telescope gave us stunning glimpses of this cosmic lensing. In the year 2006, Hubble captured a remarkable image of the Bullet Cluster, which is actually two galaxy clusters that have collided and passed through each other. X-ray images from NASA's Chandra Observatory showed that the hot gas, the ordinary matter of the two clusters, had crashed into each other and slowed down, lagging behind. But when scientists mapped the total mass of the system by observing how it lensed the light from background galaxies, they found that the bulk of the mass lay ahead of the gas, having passed through the collision without interacting. It was clear, direct proof that most of the mass in the clusters was invisible and separate from the ordinary matter. It was a smoking gun for the existence of dark matter. Dark matter does not interact with light or the electromagnetic force, which is why it cannot be seen directly. Scientists believe it interacts only through the force of gravity and possibly through the weak nuclear force. The leading candidates for what dark matter could be are hypothetical particles that are predicted by extensions of our current standard model of particle physics. These include particles called WIMPs, which stands for weakly interacting massive particles, or other particles called axions. Incredibly sensitive experiments, like the XENONNT experiment deep underground in a laboratory in Italy, and the LUX Zeppelin experiment in a former gold mine in South Dakota, are trying to detect these elusive particles by looking for the incredibly rare event of a dark matter particle colliding with the nucleus of a normal atom. So far, no confirmed detection has been made, but the quiet, patient search continues, shielded deep beneath the Earth's surface from the constant rain of cosmic rays that would interfere with the delicate detectors. Meanwhile, space-based telescopes are also searching for clues. NASA's Fermi Gamma Ray Space Telescope has searched for the subtle signature of dark matter particles annihilating each other in the dense centers of galaxies, which would produce a faint glow of gamma rays. And the James Webb Space Telescope has begun to observe the faint structures of the very first galaxies in the early universe, which formed less than 400 million years after the Big Bang. Even at that incredibly young age, these infant galaxies already showed signs of stable rotation, which strongly suggests that their dark matter halos were already in place, providing the gravitational foundation for them to form. As scientists from the European Space Agency have written, dark matter must have formed very early, shaping the universe long before the first stars ever ignited. On the grandest cosmic scales, dark matter determines not only how galaxies spin, but how the entire universe evolves. Powerful computer simulations, like NASA's Illustris project and the Eagle project, show that without dark matter, galaxies as we know them would never have formed at all. Ordinary matter would have remained too evenly spread out, unable to clump together under its own gravity against the outward push of the universe's expansion. Dark matter, being much more abundant, provided the invisible scaffolding, the gravitational wells into which ordinary matter could fall and condense. It is, as astrophysicist Neil deGrasse Tyson has put it, the greatest cosmic mystery of our time, a shadow universe holding our own in its invisible grip. Though it is invisible, dark matter leaves a gravitational trail everywhere we look. It shapes the structure of galaxy clusters. It influences the formation of the great cosmic filaments that connect them, and it even affects the rate at which the universe expands. Dark matter's immense gravity acts as a brake, slowing down the outward expansion that began with the Big Bang. This cosmic tug-of-war between the inward pull of dark matter's gravity and the outward push of another mysterious entity, dark energy, is what defines the large-scale structure and ultimate fate of everything. So, how fast are galaxies really spinning? Let us take our own Milky Way as an example. Our Sun orbits the galactic center at a speed of about 514,000 miles per hour. At that speed, it takes about 230 million years to complete one galactic year. Given the amount of visible mass that we can account for in our galaxy, the Sun and all the outer stars should have been flung out into intergalactic space long ago. But the vast, invisible halo of dark matter that surrounds our galaxy, extending perhaps 200,000 light-years beyond the visible disk, adds the necessary mass to keep it all gravitationally bound and whole. This balance between spin and gravity is incredibly delicate. If dark matter were just slightly less abundant in the teemed universe, galaxies would scatter their stars into the void. If it were slightly more abundant, they would collapse under their own immense weight. The European Space Agency's Planck satellite has made the most precise measurements to date of the universe's composition. It has found that our universe is made of about 68% dark energy, 27% dark matter, and only 5% ordinary matter. So everything we can see, every star, every planet, every person, accounts for just a tiny fraction of what actually exists. What makes dark matter so deeply puzzling is that it does not fit neatly into our otherwise incredibly successful theories of physics. We can measure its gravitational pull, we can map its distribution, and we can simulate its effects with great accuracy. But we cannot yet identify what it is made of. Some physicists have even suggested that perhaps our understanding of gravity itself is incomplete, and that on galactic scales, gravity behaves differently. These modified theories of gravity, such as modified Newtonian dynamics, attempt to explain the rotation of galaxies without the need for dark matter. But so far, the dark matter hypothesis remains the simpler and more consistent explanation for the wide range of astronomical observations. New missions are being designed to try and solve this profound enigma. The European Space Agency's Euclid telescope and NASA's upcoming Nancy Grace Roman Space Telescope will work together to map the positions and shapes of billions of galaxies, measuring how the distribution of dark matter has shaped their growth over 13 billion years of cosmic history. Their ultimate goal is not only to understand the nature of dark matter, but also to reveal how it interacts, or doesn't, with dark energy, the mysterious force that is causing the universe's expansion to accelerate. Even the James Webb Space Telescope contributes to this quest. By observing the earliest galaxies, the JWST allows scientists to test whether dark matter behaved the same way across all of cosmic time. If the formation and rotation of those early infant systems match the predictions of our current models, it will strengthen the case that the invisible hand of dark matter has always been at work, shaping the cosmos from the very beginning. It is a strange and humbling thought that what keeps the beautiful, spinning galaxies whole is something we cannot see or touch. Yet, its silent, gravitational melody is what holds the entire cosmos in tune. Without it, the universe would lose its shape, its stars flung into an endless darkness, its clusters unbound. Dark matter is the quiet, unseen architecture of existence, a grand framework made not of light, but of stability. Take a slow breath. Every star you have ever seen in the night sky, every distant galaxy that has ever drifted across the lens of a telescope, is balanced upon a foundation of something invisible. You are living in a universe that is held together by shadows, a universe governed by forces that act without ever being seen, silently guiding the motion of everything that spins. And as we trace the influence of that invisible hand through the darkness, we begin to notice something even stranger, even more intimate. If dark matter holds the galaxies together, could it also have shaped the very direction of life itself, even down to the fundamental spin of its molecules? Perhaps the same hidden force that binds the galaxies has also left its subtle fingerprint within the delicate spirals of life, a trace we are only now beginning to uncover. Every single living thing on this planet is twisted, just slightly. Your DNA, the molecule that carries the blueprint for your entire being, spirals to the right. The amino acids, the fundamental building blocks that construct every cell in your body, all bend to the left. This remarkable, universal one-sidedness, known in chemistry and biology as homochirality, is one of the deepest and most profound mysteries in all of science. It means that life, down to its smallest and most fundamental molecular shape, has a preferred direction, a built-in bias, a spin. In the world of chemistry, chirality simply means handedness. Just like your left and right hands are mirror images of each other, but cannot be perfectly superimposed, certain molecules can exist in two distinct forms, a left-handed version and a right-handed version. In most non-biological chemical reactions, both versions are created in equal amounts. But in living organisms, only one hand is ever chosen. DNA and RNA, the nucleic acids that store and transmit genetic information, always twist in a right-handed helix. Amino acids, which link together to form the complex proteins that carry out all the functions of a cell, are, with very rare exceptions, always found in their left-handed form. It is as if, long ago, at the very dawn of life, a decision was made, a cosmic coin was flipped, and life has followed that fundamental spin ever since. Scientists have spent decades trying to understand why this is. If simple chemistry alone can produce both left-handed and right-handed molecules in equal measure, then something outside of ordinary biology must have nudged life towards one side. One of the most compelling clues comes from the light of ancient stars. Light waves can be polarized, meaning they oscillate more strongly in one particular direction. In the early universe, young, massive stars emitted incredibly intense ultraviolet radiation. As this light traveled through the vast, magnetized clouds of interstellar dust, it would have become circularly polarized. According to pioneering studies conducted by research groups at NASA's Astrobiology Institute and Ames Research Center, this circularly polarized light could have had a selective effect on the molecules it encountered. One direction of polarized light could have selectively destroyed one type of amino acid more efficiently than the other. Over millions of years, in the vast molecular clouds where stars and planets form, this subtle but persistent preference could have created a slight excess of one-handedness over the other, seeding the building blocks of life with a pre-existing bias. The European Space Agency's historic Rosetta mission provided some intriguing evidence to support this theory. When Rosetta's Philae lander touched down on the surface of Comet 67P, Churyumov-Gerasimenko, in the year 2014, its instruments detected a rich variety of complex organic molecules, including the precursors to amino acids. A careful analysis of the structure of these molecules showed signs of asymmetry, hinting that a chiral bias may have existed in the raw materials of our solar system before life even began on Earth. This suggests that the fundamental direction of life's molecules could have been inherited from the chemistry of interstellar space, a chemistry that was shaped by the interplay of cosmic light and motion long before our planet had even finished forming. Another crucial piece of evidence comes from meteorites that have fallen to Earth. In the year 1969, a large meteorite fell in the town of Murchison, Australia. This meteorite was found to contain more than 70 different types of amino acids, and when scientists later analyzed them with incredibly precise techniques, they discovered a slight but significant excess of the left-handed forms. As the scientists at NASA's Johnson Space Center have explained, the Murchison meteorite is like a chemical time capsule, preserving fingerprints of the chemistry that existed in our solar system before the planets formed. And those ancient fingerprints seem to show that the universe already had a preferred molecular direction, a direction that life would later adopt and amplify. Why left-handed for amino acids and right-handed for DNA? It might be more than just a coincidence. Some researchers believe that these opposite orientations actually complement each other in a beautiful and functional way. The left-handed structure of amino acids allows them to fold into proteins that can bond perfectly and stably with the right-handed helix of nucleic acids. This forms the precise, lock-and-key biochemical harmony that sustains all of life. If you were to try and build a biological system with the opposite orientations, the chemistry simply would not work as efficiently. Still, this fundamental asymmetry did not emerge from a vacuum. It may trace its origins all the way back to the earliest quantum imbalances in the universe, the tiny fluctuations in energy and spin that occurred within the first microseconds after the Big Bang. Experiments at major particle accelerators, like CERN and Fermilab, have confirmed that some fundamental subatomic particles, such as neutrinos, always appear to spin in a left-handed direction relative to their motion. This universal-handedness, a property known as parity violation, shows that even the fundamental laws of physics are not perfectly symmetrical. In the year 1956, the brilliant physicist Chien-Shiung Wu, along with her colleagues Sung-Dao Lee and Chen-Ning Yang, conducted a historic experiment on the radioactive decay of cobalt-60. They showed conclusively that the weak nuclear force, one of the four fundamental forces of nature, does not treat left and right equally. It has a built-in preference. As Wu herself described her groundbreaking results, nature is not as symmetrical as it appears. If even the universe's most basic forces favor one spin over another, then it is not such a great leap to imagine that the molecules of life, which are governed by these forces, inherited this same cosmic preference. On Earth, this pattern of asymmetry continues everywhere we look, from the vast, swirling arms of hurricanes to the delicate, spiraling growth of seashells. Spin and asymmetry seem to be built into the very design of nature. The Coriolis effect, caused by the Earth's rotation, determines the direction of large-scale storms, counterclockwise in the northern hemisphere and clockwise in the southern. Even our planet's magnetic field has a defined polarity, a north and a south, which flips occasionally over geological time, but never loses its fundamental sense of direction. The farther we look out into space, the more this cosmic bias seems to reappear. In 2011, the astronomer Leo Shamir, whom we met earlier, analyzed the rotation of tens of thousands of spiral galaxies from the Sloan Digital Sky Survey. He found that small but statistically significant difference in the number of galaxies rotating clockwise versus counterclockwise. This imbalance suggested a large-scale directional pattern in the universe, perhaps a preserved relic of the universe's own early spin. If this finding holds true, then the very same fundamental asymmetry that governs the rotation of galaxies may echo all the way down to the molecular structures of life itself. This profound and mysterious connection between cosmic motion and biochemistry has fascinated scientists for decades. A study from the year 2021, conducted at the Tokyo Institute of Technology, ran sophisticated computer simulations of the effects of circularly polarized light on amino acids in realistic interstellar environments. They found that even a very small initial imbalance in the spin of the photons could, over time, lead to a measurable and significant difference in the molecular chirality of the amino acids. In other words, the light from stars, shaped and polarized by the rotation of the galaxy, might have literally set the direction for life before it even began. It is easy to forget that light itself carries a form of spin. Photons can have a right-handed or a left-handed circular polarization, a kind of angular momentum that affects how they interact with matter. When the light from the first stars passed through the magnetic fields of the galaxy, fields that were themselves twisted by the galaxy's rotation, that spin could have been imprinted onto the molecules that the light touched. Even the simplest dust grains floating between the stars might have been aligned and polarized by the galactic motion, causing them to scatter light in a way that favored one molecular hand over the other. The James Webb Space Telescope is now studying the complex organic molecules that exist in the star-forming regions of our own galaxy, like the Taurus molecular cloud and the Great Orion Nebula. The JWST's incredibly sensitive infrared instruments have detected a wide range of prebiotic compounds, including long carbon chains and nitriles, forming under the direct influence of polarized starlight. These groundbreaking observations strongly suggest that the chemical seeds of life naturally inherit a sense of directionality from their cosmic environment. So, When we ask whether the universe's spin decided the direction of life, the accumulating evidence points towards a quiet but compelling yes. From the spin of the fundamental particles to the handedness of neutrinos, from the polarization of starlight to the chirality of biological molecules, every scale of nature seems to possess a subtle preference for motion in one direction over another. It is as if life is not a random accident at all, but a beautiful and intricate continuation of the universe's earliest, primordial rotation, a memory that is now written into every single strand of your DNA. As the great astrophysicist and poet of science Carl Sagan once said, "We are made of star stuff." Perhaps it is also true that we are made of the spin of those stars, the angular memory of their ancient light. Take a quiet, slow breath. Every single cell inside your body still carries that fundamental twist, a microscopic echo of the universe's grand and ancient turning. From the silent, majestic dance of the galaxies to the delicate, intimate spiral of your own DNA, the same fundamental motion continues, smooth and silent, across 13.8 billion years of time. And now, as we look deeper into that profound cosmic connection, another question begins to emerge. A question not about beginnings, but about endings. If everything that spins must one day, inevitably, slow down, what happens when the universe itself begins to forget how to turn? That is the quiet, final mystery that is waiting for us ahead. Every rotation slows. The Earth's days, as we have learned, are gradually getting longer. The great galaxies are drifting apart from one another, their graceful spiral arms losing their angular momentum to the vast emptiness of space. Even the stars themselves, those magnificent furnaces of motion and nuclear fusion, are burning down, one by one, their fires slowly dimming over eons. The universe that began with a great, violent, primordial spin seems to be slowly, inexorably unwinding. But can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the expanding fabric of space, like a drop of ink in an infinite ocean? The NASA physicist Michelle Thaler once said, "Energy doesn't disappear, it just disperses." So too, it seems with spin, it does not simply stop, it diffuses. Our own planet, for instance, is already losing its youthful rhythm. Each century, the constant gravitational pull of the moon creates a tidal bulge on the Earth, and the friction of this bulge as the planet rotates beneath it acts as a subtle brake, slowing our spin by about 1.7 milliseconds. This energy is not lost, it is transferred to the moon, pushing it into a slightly higher orbit. As a result, the moon is drifting away from the Earth by nearly 1.5 inches every single year. This gentle, cosmic dance of tidal deceleration has been going on for billions of years. The laser reflectors that were left on the lunar surface by the Apollo astronauts have allowed scientists to confirm this drift with millimeter-level precision. If this process continues uninterrupted, the Earth's rotation will one day slow down so much that it will become tidally locked with the moon's orbit. One side of the Earth will perpetually face the moon, just as one side of the moon already perpetually faces us. It will mark the end of the tides as we know them, the end of the daily cycle of ocean and air that has driven our planet's climate for so long. The planet's spin, once vibrant, will have faded into a state of quiet equilibrium. Elsewhere in our solar system, the same slow story is playing out. The planet Mercury is already trapped in a 3-to-2 spin-orbit resonance, meaning it rotates on its axis exactly 3 times for every 2 orbits it completes around the Sun. Venus, with its incredibly dense atmosphere that creates immense friction, has slowed to an almost unearthly crawl. One rotation of Venus takes 243 Earth days, and strangely, it spins in the opposite direction of its orbit. Even Mars, whose day is currently only slightly longer than our own, is gradually losing its rotational speed. Over the vast timescales of the cosmos, spin is not forever. It is a rhythm that is slowly, but surely, winding down. This slowing process continues beyond the scale of planets, out into the heart of the galaxies. Using powerful instruments like the Hubble Space Telescope and the Very Large Telescope in Chile, astronomers have measured the rotation speeds of spiral galaxies that are billions of light-years away. When they compare these ancient galaxies with the modern galaxies we see closer to us, they find that the ancient systems appear to have spun faster. They had tighter spiral arms, denser cores, and more concentrated angular momentum. As time passes, gravitational interactions between galaxies and the overall expansion of the universe gradually sap that motion. According to a study from the year 2020 from the Leibniz Institute for Astrophysics in Potsdam, Germany, galaxies can also lose a significant portion of their spin through collisions and mergers. When two galaxies merge, their individual stars rarely collide, as the distances between them are so vast. But their huge, invisible dark matter halos do interact, and this interaction can redistribute angular momentum outward into the new, larger halo. This process tends to leave the resulting galaxy rounder, slower, and more diffuse. The graceful, spinning spiral gives way to the slow, stately, elliptical galaxy. The European Space Agency's Gaia mission, which has mapped the motions of over 1.8 billion stars in our own Milky Way, has revealed that even our galaxy is evolving towards a state of greater stillness. Its outer arms, which were once more tightly wound, are gradually stretching and unwinding. Over the next few billion years, the gentle friction with its own dark matter halo and the gravitational pull of nearby galaxies will continue to drain its spin, softening its beautiful spiral form. Eventually, our Milky Way and our nearest large neighbor, the Andromeda Galaxy, are destined to collide. This will not be a violent, chaotic event, but a slow, silent fusion that will take place over hundreds of millions of years. Their combined rotation will eventually settle into a single, massive, and nearly motionless elliptical galaxy. But spin does not simply vanish when the stars begin to fade. It transforms. When a massive star reaches the end of its life, it collapses inward under its own gravity. As it collapses, it conserves its angular momentum, and just like that figure skater pulling in her arms, it begins to spin at incredible speeds. This process creates neutron stars, those city-sized objects that can rotate hundreds of times every single second. NASA's NISA instrument on the International Space Station has observed pulsars spinning as fast as 716 times per second, their powerful beams of radiation sweeping through space with the precision of the best atomic clocks. Yet, even these cosmic lighthouses, these ultimate spinning tops of the universe, eventually slow down. They radiate away their immense rotational energy in the form of powerful magnetic fields and, more subtly, as gravitational waves ripples in the fabric of space-time itself. As time expands even further into the truly deep future, rotation will become a rarity. The stars will fade and die, and the black holes, those last great engines of spin, will themselves slowly evaporate through a process known as Hawking radiation. In the year 1974, the brilliant physicist Stephen Hawking predicted that even black holes are not eternal. They leak a tiny amount of energy and, over unimaginable timescales, will lose their mass and their angular momentum. A spinning Kerr black hole will gradually transfer its rotation to the surrounding space, leaving behind faint, fading ripples of energy that stretch out across the universe. The European Space Agency's planned LISA mission, a space-based gravitational wave observatory set to launch in the 2030s, will be sensitive enough to detect these gravitational whispers, the waves created by spinning black holes as they merge and eventually fade away. Each detection will be a record of rotation being released back into the fabric of space-time, a final echo that will ripple across billions of light-years. Even when the black holes themselves are long gone, their rotational memory will remain, imprinted forever in the very geometry of the universe. So, will the universe ever truly, completely, stop spinning? The answer is likely no. not completely. The fundamental law of physics states that angular momentum cannot be created or destroyed, only transferred. It will be spread, thinner and thinner, shared among an ever-expanding sea of low-energy particles. As NASA explains, in an isolated system like the universe as a whole, the total angular momentum is conserved. In this sense, the universe never really stops moving. It only redistributes its motion until it is almost imperceptible. Still, there may come an age so far in the future that it is beyond human comprehension, a time when motion becomes functionally meaningless. In this far future, long after the last stars have died and the galaxies have faded into darkness, the universe will enter what physicists call the heat death. Energy will be evenly and thinly distributed everywhere. There will be no temperature gradients, no flow of energy, no reason for anything to happen or to move. Rotation will still exist in a purely mathematical sense, but without any contrast or structure, it will have no meaning. Some cosmologists, including Lawrence Krauss and Brian Greene, describe this final state as the ultimate cosmic silence. The final, perfect calm after every last vibration, every last orbit, every last spin has faded away. In that distant, dark epoch, protons themselves may have decayed, and the last black holes will have evaporated into a final burst of radiation. Only faint, cold background photons and ghostly neutrinos will drift endlessly through the dark, expanding space, carrying with them the last, infinitesimally small traces of the universe's once grand and glorious rotation. The James Webb Space Telescope peers deep into the past, but in doing so, it also reminds us of the universe's ultimate future. Every ancient, fast-spinning galaxy it observes is another tick backward on the cosmic clock, showing us a time when rotation was more vibrant, a time when it was the primary force defining structure. In its breathtaking images, we can see both the beginnings and the endings of motion, motion kindled by a broken symmetry, and motion destined to fade into a final, profound stillness. Even so, spin leaves behind fingerprints that cannot be completely erased. From the subtle polarization of the cosmic microwave background to the final, lingering curvature of space-time around the ghosts of long-dead stars, the memory of motion will remain encoded in the universe's fundamental design. It is not the movement itself that we will lose, only the strength, the contrast, to be able to notice it. Take a long, slow breath. Right now, in this moment, the Earth's liquid core still turns, the stars still wheel in their orbits, and the Milky Way still drifts in its majestic spiral through the endless darkness. Every motion you know, every rhythm you feel, is a flicker of that ancient, primordial rotation, one that will outlast you, but will not outlast eternity itself. And when that eternity finally arrives, when the last spin has finally stretched into a perfect and profound silence, something else will still remain. Not movement, but the memory of movement. Because even when the universe forgets how to turn, its very geometry will still remember that it once did. As we approach that distant horizon of ultimate stillness, another, more intimate question quietly unfolds. If every atom, every planet, and every galaxy is slowly, inevitably, winding down, what does that make us? We, the ones who are still moving within it. That is where our final story begins. With a motion not of the cosmos, but of consciousness itself. Every single atom inside your body is spinning. The electrons that orbit your atomic nuclei, the protons and neutrons that make up those nuclei, and the quarks that are bound deep within them all, are caught in a state of ceaseless, fundamental motion. That motion is not random. It is a continuation. It is the faint, preserved echo of the universe's very first rotation. When you move, when you breathe, when your heart beats its steady rhythm, you are not performing an action that is separate from the cosmos. You are participating in its oldest and most enduring memory, the memory of motion itself. In the language of physics, Angular momentum is the principle of the persistence of spin, the fundamental rule that keeps motion alive across the eons. It is the reason why galaxies still turn, why planets still hold to their orbits, and why atoms still vibrate with energy after 13.8 billion years of cosmic history. According to the scientists at NASA's Goddard Space Flight Center, angular momentum cannot be destroyed. It can only be transferred or shared. This profound law means that every single spin in the universe, from the grandest galactic spiral to the smallest quantum flicker, is a direct continuation of the same original rotation that began at the moment of the Big Bang. In the very beginning, the universe was not still. As we have seen, the precise measurements made by the European Space Agency's Planck satellite show that the cosmic microwave background, that faint afterglow of creation, carries subtle anisotropies, slight directional differences in temperature and polarization. Some cosmologists interpret these ancient patterns as the preserved traces of the universe's first angular momentum, the original, primordial twist that set everything into motion. That primordial spin never vanished. It fragmented, cascading down through the scales, spreading from the universe as a whole to the individual structures within it. When stars form, vast clouds of hydrogen and helium gas collapse under the relentless pull of their own gravity. As they shrink, they begin to rotate faster and faster, perfectly conserving their initial angular momentum, just like that ice skater pulling in her arms. This same simple but powerful rule gives rise to the swirling accretion disks we see around young stars, the flat planes of our planetary systems, and even the chaotic, spinning whirlpools of matter that feed supermassive black holes. Carries within its orbit and its own rotation a small, preserved fragment of that initial cosmic spin. And within those planets, inside every rock, every ocean, and every living cell, the pattern of rotation continues on ever smaller and more intimate scales. Our atoms, too, hold this rotational memory. The electrons that define the chemical bonds that hold your body together obey the strange quantum property of spin. This is a fundamental, intrinsic angular momentum that is a property of all fundamental particles. As we've noted, this is not a literal spinning like a tiny ball, but a fundamental quantum state, a value that determines how particles interact with magnetic fields and with each other. Without the property of quantum spin, chemistry as we know it would not exist. There would be no stable atoms, no molecules, no life. The scientists involved in NASA's Quantum Laboratory Initiative describe spin as the very engine of atomic structure, the fundamental difference between a universe of inert chaos and one of ordered stability. In this sense, you could say that every single piece of matter in the universe carries with it an ancient choreography. The spin of fundamental particles leads to the existence of magnetic fields. These fields lead to the formation of stable structures. These structures lead to the birth of stars and planets. And ultimately, this chain of events leads to the emergence of life. The very neurons in your brain fire using electrical potentials that are shaped by these same fundamental fields. Every single thought that crosses your mind is, at its most basic level, a complex and ordered alignment of charged particles, a kind of ordered, coherent motion. So when we ask whether consciousness might be the universe remembering its own motion, the question is not merely poetic, it is deeply physical. Each brainwave, each neural signal, is built upon a foundation of quantum rotations that have existed since the very dawn of time. The faint magnetic fields generated by your own brain are subtle echoes of the same fundamental electromagnetic principles that guide the immense power of pulsars and magnetars. As the astrophysicist Neil deGrasse Tyson has so eloquently said, we are not in the universe, we are part of the universe, and the universe is in us. From a purely scientific perspective, memory is a form of pattern preservation. It is information that is encoded into a physical state. In this sense, atoms can be said to remember through their spin orientation. Cells remember through the complex structure of their molecules. Stars remember their formation through their rotation curves. and the universe itself remembers through the very geometry of space-time. Einstein's theory of general relativity teaches us that the distribution of energy and momentum is what shapes the curvature of space-time. Every movement, every rotation, leaves a small, indelible indentation, a subtle swirl in the fundamental geometry of reality. This is the phenomenon of frame dragging, which was confirmed by NASA's Gravity Probe B experiment in the year 2011. That incredible mission measured how the Earth's own rotation subtly twists the space-time that surrounds it, like a spoon gently stirring honey. It was the first direct proof that spin is not a property that is confined to objects alone. It extends out into the very fabric of the cosmos. In a similar way, even your own movements, though infinitesimally small on a cosmic scale, also disturb the fabric of space-time, ever so slightly. The only difference is one of scale. The atoms within your body spin billions upon billions of times per second, generating tiny magnetic interactions that can be measured by sensitive quantum sensors. Each one of these micro-rotations contributes to the ongoing, unbroken record of motion that began long before humanity, or even the Earth, existed. If all motion leaves its traces in the fabric of space-time, then perhaps what we call awareness, what we call consciousness, is simply the way that the universe perceives those traces through us. Not as an emotion or a spirit, but as a deep physical continuity, as matter recognizing its own incredible persistence through time. Consciousness, in this purely scientific sense, could be seen as a system's capacity to reflect and model its own internal state. And that reflection is written in the language of movement. Even light, the great messenger of the cosmos, carries angular momentum. Photons possess a quantum spin value of 1, which determines how they can be polarized and how they interact with matter. The polarization patterns that we can still detect today across the cosmic microwave background act as the oldest and most profound record of rotational memory in existence. The European Space Agency's Planck satellite and NASA's WMAP mission mapped these faint, ancient swirls in exquisite detail, showing us the subtle B-mode patterns that may be the signatures of primordial gravitational waves rippling out from the universe's very first, violent motion. So when you gaze up at the starlight in the night sky, you are literally seeing the memory of spin. You are seeing light that has been twisted, stretched, and polarized by 13.8 billion years of cosmic motion. And that ancient light enters your eyes, triggers a cascade of chemical reactions in your retina, and becomes a part of your own neural motion. In that very real, physical way, the universe does not just remember its own spin. It continues to experience it, to relive it, through every single observer it creates. Even as the cosmos continues its long, slow expansion and cooling, these traces of motion persist. The galaxies may slow their spin, but their total angular momentum never truly disappears. It is passed on to the thin intergalactic gas, to the vast dark matter halos, to the radiation that streams out into the void. The James Webb Space Telescope has detected faint, ghostly filaments of gas stretching between the most ancient galaxies, vast cosmic structures that were shaped by these very transfers of spin. Every wisp of matter in the universe still moves to the ancient rhythm that was set at the very beginning of time. And when the last stars have finally faded, and all motion has quieted into a deep and profound silence, those patterns that have been encoded into the final gravitational waves, into the spin of the last remaining particles, and into the frozen light of the cosmic background, will still ripple faintly through the empty, dark space. They will not be gone. They will be written into the final shape of everything that remains. Like the delicate fossils of motion, they will form the universe's deepest and most enduring kind of memory, motion preserved as pure geometry. The great Carl Sagan once reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the language of modern physics, that knowing is not mystical. It is enacted through the principles of motion, energy, and spin. The universe is a system that is continuously encoding and retrieving its own history. Take a slow, final breath. Let it fill you. Every atom inside you continues to turn, carrying the same fundamental spin that once ignited the first stars. You are a moving archive, a living, breathing part of the universe's ongoing, 13.8 billion-year-old memory. And as we follow this idea to its quiet conclusion, this thought that motion may be the cosmos remembering itself, a new and final horizon opens before us. Because if memory is movement, then perhaps what we call life is simply the brief, precious moment when the universe pauses, just long enough to notice that it is still spinning. Close your eyes. The silence you feel is not stillness. It is the universe remembering how to move. If this quiet journey has brought you even a small moment of peace or wonder, I am deeply grateful that you have spent it here with me. A gentle like on this video, or a soft tap on the subscribe button, means more than you can possibly imagine. It is what keeps me creating these cosmic lullabies for wandering minds like yours. And if you feel so kind, please tell me in the comments below where you are tonight, and what time it is in your part of the world as you are listening. I love to see how far these quiet adventures drift across our spinning planet, from one sleepy corner to another. Your words, your presence, and even your silent listening, they are like little stars that guide me forward, and I treasure them all deeply. Until we meet again, may the universe turn softly and quietly around you.